Next, I would like to introduce Dr. Nusrat Jung, an assistant professor at Purdue University in civil engineering. Professor Jung leads an interdisciplinary research team that focuses on the identification, characterization, and mitigation of harmful pollutants like VOCs, or volatile organic compounds, and fine particulate matter, which have critical health implications. She is, and I can say this because I've worked with her, she is highly skilled at developing new, never before used sampling methods to support disaster response, emphasizing the importance of time-sensitive environmental contamination assessments for public health and safety decisions. And so with that, Professor Jung, thank you for joining us. The floor is yours.
Thank you so much, Professor Welton, and good morning, everyone. Thank you very much for joining us today to hear about our work. I'm going to quickly share my screen. Is this visible to everyone?
Yes.
Yeah. So thank you again for being here today to learn about our published results. My presentation will focus on sharing a novel screening method that we have developed to rapidly detect volatile organic compounds in water samples to support decision-making during the case of a disaster, and to intent is to protect public health whenever such a situation occurs. So this brings us to a question as to why do we need a rapid volatile chemical screening method? Well, the hazardous chemical incidents, including fires, explosions, and chemical releases, are occurring every 2 days in the United States. So this is happening way more often than we hear about. Around 172,000 chemical spills have affected water bodies in the US between 2004 and 2014. So think about it. I'm talking about 2014. This is the recorded number we have. So the actual number is far greater. Whenever such an incident occurs, local emergency services initiate the response, and then they contact federal agencies if the disaster exceeds the local capabilities. So from our point of view, coming from Purdue University, together with Professor Welton, this immediate evaluation of exactly what happened and what kind of chemicals have been released into the system to, by system I mean the environment, soil, water, air, within the communities where we live, is very important step. If we can evaluate truly what may be wrong, we can actually help, we can respond better to ensure our well-being. So we have a paper published in Science of the Total Environment that is presented on the right side of the screen. This is the name of all the listed research team members who worked very hard in creating this method, and not just that, but most importantly, collecting the samples. We are very grateful to people of East Palestine who helped our team, and especially Professor Welton's team, who were there on site collecting these samples for us to further analyze. So what is so special about this method? So historically, several techniques have been used to monitor air and water composition after chemical incidents. And typically, many of you may be aware of something called as a photoionization detector. PIDs, they are handhelds, and they are sometimes used for volatile organic compound sampling. It is typically due to their low cost. They are also portable, and so on. So there are many methods that are out there that are used, but we want to talk about why do we really need a rapid method that is more accurate. So here is a conceptual framework that we would like to provide. So in case of a chemical disaster where we need to identify environmental and public health risks more rapidly, we can use sophisticated techniques such as PTR-TOF-MS. PTR-TOF-MS stands for proton transfer reaction time of flight mass spectrometer. to conduct a very controlled headspace sampling inside a mobile vehicle to provide high quality information that can generate a mass spectra. Mass spectra is something that you see on the screen. You see a mass to charge ratio and a mixing ratio. And this can actually provide you with information of what volatile chemicals may be present in the environmental media to facilitate emergency response to support disaster relief. So honestly, the information is really important of what has been released. If we have that information, we can actually help. But whenever this information is delayed, it becomes harder and harder to understand how deep or big the problem may be. So what did we do to develop this and validate our method? On this slide, we see that we collected around 20 surface water samples from 16 sites alongside Sulphur Run, Leslie Run, Bull Creek, North Fork, Little Beaver Creek, and around the train derailment site. The train derailment itself occurred approximately 30 meters away from Sulphur Run. Sulphur Run flows into Leslie Run and it subsequently merges with Bull Creek. The flow continued into the North Fork, Little Beaver Creek, and this is what feeds into Little Beaver Creek before ultimately merging into the Ohio River. So for this particular study, our lab used very stringent quality assurance and quality control when preparing samples and sampling the headspace volume. We used high performance vials and septa, so we want to make sure there's no other contamination that can come through the method into an already contaminated water sample. It's very important to do this work carefully. We then placed the headspace sample in lab for about 1 hour to reach ambient temperature. So the reason this is rapid is because we do not need to prepare the sample in a traditional sense. We don't need to heat it. We don't need to add any chemicals to it. We don't really need to anything. We really need to put it in a vial and let it sit in the lab to reach ambient temperature before analysis. For this particular study, we used hydronium ion as a reagent ion, and we conducted triplicate of each sample, which was prepared and analyzed. So what you see here are some of the results. The headspace analysis of the water samples, it consisted of 3 steps. We had first the purge for 1 minute, then an equilibrium for 60 minutes, and then static headspace sampling for about 15 seconds. So based on the equilibrium that was established in the previous step, the measurement of the static headspace concentration allows for the estimation of aqueous volatile organic compound concentrations based on Henry's law. So for example, here in the left-hand corner, you see raw signals in count per second of 2 different compounds with mass to charge ratio of 57.033 and 57.070. This shows that the sampling is stable and it is a constant signal. It also shows an excellent mass resolution, enabling detection and separation of the peak within the same mass to charge ratio. The average of the VOC signal detected during this 5-second plateau was taken for further analysis. So this is really important to understand when you're using a handheld photoionization detector. It is providing you with a total VOC concentration. So you don't have the ability to actually speciate what are you looking at. You just get one value, but you honestly don't know the composition of what is that value. So the separation of peaks or the understanding of what is the emission composed of is extremely important for decision making. In this slide, we show mass spectra of selected water samples. The first 2 that you're looking at are sulfur run downstream of the train derailment site. You will note that over 200 or more ions were detected, while the background water sample from 5 kilometer upstream, which is in the bottom, shows a smaller number of ions. So 5 kilometers is around 3.1 mile radius. So really what you can see here is that the water is more contaminated around the derailment site than it is outside that area. Here it gives you more understanding of showing the spatial variation in the chemical composition of samples that were taken within the 3.2 kilometer radius of the train derailment site. What we see here is that hydrocarbons dominated the chemical composition of all surface water samples, contributing to around 50% to 97% of the total VOC mass concentration that are detected in the headspace air. So the spatial variations in the chemical composition of the surface water samples can be observed, and you will see that the silicon-containing compounds contribute more to the total VOC mass concentration at the more downstream sites. If you look at the composition of surface water outside the area, you'd notice that the chemical composition of surface water samples collected from the sites inside East Palestine is more complex as compared to what we collected further from East Palestine. So VOCs that are frequently reported in surface water samples predominantly are aromatics, benzene, styrene, xylene, and they have been all detected at different mass charge ratios in all of the water samples, except perhaps one, I think it was C16. So in summary, because this is a short presentation, I want to share really that we developed a controlled static headspace sampling system in conjunction to a high resolution proton transfer reaction time of flight mass spectrometer. This is a new technique that can enable rapid screening of VOCs in water samples. It can support fast response to chemical disasters and environmental hazards to protect human health and the natural environment. It is very important to know that when such disaster happens, we really want to be able to make informed decisions. And we can make informed decisions if we have an understanding of what is the problem we are looking at. So we hope that in the future, this method can be used and deployed in a possibly scaled. The paper is open access. We invite you all to read it and learn more about it, use it, and deploy it. We really hope that this will help advance our understanding of how sophisticated tools can support a rapid response for disaster relief. That is the end of my presentation. Thank you very much for your attention, and I look forward to taking any of the questions you may have during question and answer session. Thank you.